In this lesson, we will discuss the difference between the Lagrangian and Eulerian descriptions of fluid flow. When analyzing the performance of devices using control volumes, we only need to know the flow details along the control volume surface and are not required to know the details of what happens inside the control volume. However, there are many situations where knowing the details of the entire flow at every point in the region of interest is necessary. Some examples include trying to reduce drag on a race car, trying to enhance the mixing of air and fuel inside an engine cylinder prior to combustion, and trying to ensure inhaler medication penetrates deeply into the lungs. A large body of fluid consists of many fluid elements. A fluid element is a very small parcel of fluid. Although there is no official size of a fluid element, think of it as a chunk of fluid that is smaller than your eyes can see, but is still made up of many molecules. There are two points of view from which we can examine the motion of fluid elements. The first viewpoint is called Lagrangian, in which each individual fluid element is tracked in time. Here we have 4 fluid elements off the west coast of California. In the Lagrangian viewpoint, the equations of motion of these 4 fluid elements are well known from dynamics, simply F equals ma. However, it would be too difficult to try to keep track of all the fluid elements that would be present over California at a given time. To make matters more complicated, the fluid elements can deform, mix with other fluid elements, and split into new fluid elements as they move through space. The second viewpoint is called Eulerian, in which the fluid elements are observed at fixed points in space. For example, we could build multiple observation stations in California and record the properties of the fluid elements as they travel past the stations. At the moment, we don't know the equations of motion at every point in space from the Eulerian point of view. We will develop these equations in future videos, and they will turn out to be more complicated than F equals ma. One of the main benefits of using the Eulerian viewpoint is that it is usually much more convenient to conduct experiments by observing specific points in space compared to tracking numerous particles as they flow through space, which is the Lagrangian viewpoint. The Eulerian description of flow uses scalar fields and vector fields to describe fluid properties. Weather forecasts are reported using the Eulerian viewpoint. For example, on the right is the temperature distribution in Fahrenheit across California at a specific time. Temperature is a scalar quantity, and it is reported for many locations, not for individual fluid particles which move from location to location. So temperature can be thought of as a scalar field that varies with both position and time. On the left, we see wind velocities across California at a specific time. Wind is reported for various locations, not for individual fluid particles which move through space. Wind can be thought of as a vector field, and its components, lowercase u, lowercase v, and lowercase w, all can vary with position and time. Notice that in the Eulerian point of view, the coordinates x, y, z, and t are all independent of each other. However, in the Lagrangian point of view, a fluid element's position is described as a function of time. Here we see a fluid element, labeled A, in a Cartesian coordinate system. From the Lagrangian viewpoint, the fluid element's current location is xa, ya, za. Since the fluid element's location can change in time, xa, ya, and za are functions of time. This means the velocity of the fluid element, va, can be thought of as just a function of time. Now let's imagine someone is taking the Eulerian point of view and observing a specific location in space, which we will label x, y, and z. At this moment in time, both x, y, and z and xa, ya, za happen to coincide with each other. This means that the velocity of fluid element A from the Lagrangian point of view, which we call va, is the same velocity as seen by an observer from the Eulerian point of view, which we call v. As we discussed earlier, in the Eulerian viewpoint, velocity is a function of position and time. After a small time dt has passed, the fluid element has moved to a new location and has a new velocity. We still refer to the fluid element's coordinates as xa, ya, za in the Lagrangian description, but these coordinates no longer coincide with the original location x, y, z in the Eulerian description. The velocity at xyz may change as well due to new fluid elements entering the region.